IBS seminar. Today our speaker is Professor Janos Asboth from Budapest University of Technology and Economics. So let me introduce him a little bit. So he finished his PhD from Innsbruck University, Austria in 2008. And then he moved to the Leiden University as a postdoctoral researcher. After that, he joined as a research fellow at Ugner Research Center, Budapest. He is currently also affiliated there, and he simultaneously started his new position as an associate professor in Budapest University of Technology. He was awarded by many prestigious prizes. So today he's going to talk about his topological delocalization in the completely disordered two-dimensional split-step quantum walk. Let's welcome the speaker.
Thank you. Thank you, Arindam. Can you all hear me?
Yes, yes, everyone.
Okay, great. So thank you very much for this kind introduction. And thank you for the opportunity to present my results, our results to you. When I say our results, this is in a large part about work which I did together with Arindam, a project which started when Arindam did a short research stay in Budapest last year. And so this talk is going to be about topological delocalization in the completely disordered two-dimensional split-step quantum walk. In the left, you can see animation showing how a quantum walk spreads. And what the animation shows is kind of a diffusive spread. You can see how the wave function increases, and you can see how the root mean square displacement grows over time as the square root of time. So this is indicative of diffusion. So you might be wondering, if this is a quantum walk, why does it spread diffusively? Or if you're not wondering about that, you will be wondering about that by the halftime of this talk. And if all goes well, then by the end of this talk, you should be able to understand why this is interesting and why and when it happens. So this work was the work with Arindam. We submitted to Physical Review B. It's under review, and it is on the archive at the given link. So quantum walks, in your research group, some people are working on quantum walks, but maybe some people are less familiar with quantum walks. Quantum walks are interesting for quantum information and condensed matter. They explore the Hilbert space, but spread faster than classical random walks, not diffusively, but ballistically. So this is a square root speedup, the same square root speedup which is behind the Grover algorithm. On certain special graphs, this turns to an exponential speedup. Quantum walks can also realize a universal quantum computer, and they can serve as a controlled toy model for decoherence, Dirac equation. An early example is shown in the lower left. So this is from a paper from 2002, Wolfgang Dürr and co-authors, where they added some degree of decoherence to the dynamics. And what is shown is a snapshot of the wave function of the quantum walker. This is a one-dimensional quantum walk after a fixed amount of time. So you can see that without decoherence, the wave function looks nothing like the usual random walker, which would have just a Gaussian whose width increases like the square root of time. Instead, we see two peaks. These two peaks, they move away ballistically, so they are quite far away already. But as you increase the amount of decoherence, you get a gradual transition to classical random walk behavior with a Gaussian probability distribution. So today we're not going to talk about one-dimensional quantum walks. We're going to do two-dimensional quantum walks, but we take the simplest two-dimensional quantum walk. So we have two internal states. You can think of an electron with a spin, for example, which is sitting on a square lattice. And instead of having a Hamiltonian, which governs the time evolution, we're going to actively interfere in the system, and the time evolution is dictated by a sequence of unitary operators, a periodic sequence of unitary operators. So there are two types of operators, a spin rotation and a spin selective displacement on the lattice. So we rotate the spin about some axis through some angle. These are parameterized by these operators R, which are defined in the lower right. And then we do a conditional east-west shift where the shift of the direction depends on the value of the spin. Then we do a second rotation, a conditional north-south shift. And at the end of this period, we can also shift the phase by phi. So shifting the phase, you might think it is nothing special, just multiplying the wave function by a global phase doesn't show up in almost any of the observable quantities. Things will become more interesting if this phi will depend on position or on time. In any
Sorry,
case,
Janos, there's a question. Igor, please go ahead.
Hello. So I'm wondering why you're calling this the simplest two-dimensional quantum walk. Isn't an option with a single rotation, so kind of merged part 1 and part 3 and merged part 2 and part 2 and part 5 is a simpler option?
you could do with a single rotation, but in that case, two internal states would not be enough. So you need, if you just want to use two internal states, which is simplest from that point of view, you need to split this step.
I see. Thank you.
Welcome. And happy to have questions anytime during the talk. Okay, so the wave function of the Walker spreads over the lattice. An example is shown here. I chose some fixed angle for the rotation and some fixed angle for the rotation axis, and the rotation is by 0.2 pi, 0.4 pi. So you can observe that the wave function spreads ballistically. This is shown also below the plot, and you can also see how the wave function spreads with the probability concentrated at the fringes. And this behavior, both the ballistic spread and the fact that most of the weight of the wave function is at the front of the propagation, can be understood by representing the unitary time evolution operator as e to the minus ihf with some effective Hamiltonian, which is defined as the logarithm of u. And then formally, what the quantum walk is a stroboscopic simulation of the time-independent Hamiltonian hf. So this is formally a solution of the time-dependent Schrödinger equation with a fixed Hamiltonian. So then, if hf describes a lattice system, then there will be a maximum of the group velocity, and there will be a higher number of plane waves with that group velocity. So this explains why the ballistic spread, and also explains what the velocity of the ballistic spread is.
Sorry, Janos, I have a question.
Please.
Do you know about an example of such an effective Hamiltonian for even maybe a one-dimensional quantum walk?
So you can construct the effective Hamiltonian. It will not be very pretty. So
Right. In particular, I'm interested in understanding that is still a lattice, right, on which we define the Hamiltonian. So that means that we have to write down what, some kind of hopping network.
Some kind of hopping Hamiltonian.
And how will that hopping be? Will that be long range, short range? What can we say about that hopping?
So what we can say is that it is not finite range hopping. So there are hoppings of arbitrarily long distance, but their amplitude decreases exponentially. So it's
but then one would expect. So you want to say it's kind of short range hopping still?
Yes, in some sense, it's short-range hopping still. Yes, the dispersion relation is analytical, so therefore the hopping amplitudes have to decrease exponentially.
Thank you. Fair point.
Okay, you're welcome. So now I want to ask you a question. What happens if we use this, if we let this phi, this phase phi, be a randomly fluctuating quantity? So it is random equidistributed between 0 and 2 pi, and new values are drawn after every time step. So it is a stochastic function of x, y, and of t. How does the quantity look in that case?
Sorry, Janos, another question. Mera, please.
Yes, sorry, it was late, I guess. So in the previous slide, you showed that you said that you have some evolution which is dictated by time-independent Hamiltonian. So my question is, we could expect some sort of energy expression for quantum walks, or what could I measure as an analog of energy in the quantum walk simulation?
Yes, yes. So there's a quantity called quasi-energy. So because the effective Hamiltonian is defined by this formula, this means that if I take any of the eigenvalues of the effective Hamiltonian and add 2 pi to it, then the effective Hamiltonian is unchanged. So this is similar to the situation of, to the relation between true momentum and quasi-momentum. For a particle which is which lives on a lattice, if its wave function, if the phase of its wave function changes by 2 pi from one lattice side to the next, then I can't distinguish this from no phase change at all. So a quasi-momentum of 2 pi over A is the same as 0 over A. Likewise, with the quasi-energy value of 2 pi over capital T, where T is the time period, but we're going to use dimensionless units here, so the time period is always 1. So quasi-energy of 2 pi is the same as 0. And this quasi-energy is conserved.
Yeah. Okay, thank you.
So
I'm sorry, I still also
please.
have a question. Well, if I talk about conserved quantities, say an energy for a Hamiltonian problem, then I would know what to do. I will take the evolution and I will calculate the expectation value and show that it is constant. For right now, how do I do that? How do I do that here?
So you could also take for example, the expectation value of the effective Hamiltonian, and this cannot change over time.
I say I don't know that Hamiltonian, but I do know that there is one. So how can I proceed then?
You can derive. So this formula HF is I ln U. This is a constructive formula. So if you know what U is, then you can just you can derive the effective Hamiltonian. It's not. I mean, it's not necessarily going to be a pretty function, a pretty matrix. Like if you want to get the analytical formula, it might be ugly. I never derived it, so I derived the eigenvalues as a function of momentum for the translation invariant case, and they are kind of okay. They are not too bad. So arcus cosine, and whatnot.
Thank you.
So now I'm asking you a question, the audience. What do you think? What happens if we had this ballistic spread here? What happens if we modify time evolution by making the quantity phi fluctuate?
Well, you will get the coherence.
We get the coherence, and as a result,
Diffusion, I expect.
pardon?
I would.
It's less than 1. It's not just the color tells you, the shade tells you that the wave function is no longer there. Okay, but you see that it spreads diffusively. This is just an illustration, but it actually does spread diffusively.
Oh, Janos, Alexia has a question, I think. Go ahead.
Yeah, thanks. Sorry, that's basically a continuation. So, and I might have asked something similar during your previous talk. What happens if instead of completely random phase, you take a quasi-periodic phase in time?
Yes, my opinion is that the rough picture would be the same, but there might be some extra structure. I didn't, I'm not quite sure. I didn't consider this this opportunity, this problem. Overall, I would expect to still see diffusion, but there could be something else as well.
Do you think you will get diffusion for any type of quasi-periodic noise that you add, or there could be something different?
It's that's an interesting question. I'm not quite, so I'm not really sure what to expect. I didn't. So I worked a little bit with quasi-periodic stuff, but not a lot. So I'm not quite sure.
Okay, so let me perhaps elaborate a bit more. That's not really a question, just a comment. So I mean, when I was asking that, I'm basically thinking, say, if you take just Anderson problem, you know that in 1D everything is localized. So if you now take quasi-periodic potential in 1D, you will get delocalization transition. But say if you now take still quasi-periodic disorder, but different, something like Fibonacci sequence, you discover that the very same chain would just be sitting at the criticality. So you will get multifractality for any disorder strengths, well, quasi-periodic disorder strengths. So that's why I was asking what happens if you add various quasi-periodic phases here.
Yes, so I followed a little bit the literature on this one-dimensional quasi-periodic things, especially the discussion about their topological phases. But so as far as I understand, much of these effects can be understood by mapping it to a two-dimensional system, where you take slices of the two-dimensional system to obtain the one-dimensional system. But but I'm not quite sure how it works in the time on the time axis. It's an interesting question. I don't know the answer.
Okay, thanks.
Thank you. Okay, so what happens if we now randomize this phase, let it be an onsite, let it be a random function of position, but does not fluctuate in time. And already in the previous section, previous question, I heard, or previous comment, I heard that in 1D we have Anderson localization, and also in this two-dimensional system, generically we expect to see Anderson localization if there is no special symmetry of the system, and there are no special symmetries here. So this is actually what we see. This is an illustration, some finite time evolution. What you can tell is that the static disorder case spreads much less than the fluctuating case. Notice the different root mean square displacement scales for the middle and for the right plot. And you can also see that it kind of flattens out. It's not easy to tell if it's square root of time or maybe some other power of time like subdiffusive behavior, but over longer time evolutions it becomes clearer, and then you can rely on other tools to convince yourself that this is really Anderson localization, which we did in the paper with random. So what we see is that for generic quantum walks, static disorder induces Anderson localization and stops their spread. So a quantum walk was more efficient than a random walk in the translation invariant case. It was just as efficient as the random walk in the fluctuating case, and it was much less efficient than the random walk for the static disordered case. So it's an interesting scenario.
Sorry, Janos, I don't see localization in your plots.
Yes, so what you can see here.
Where do I have to look at?
Yes.
At the right plot? Is that what you?
The right plot is the static disorder. the middle plot is the fluctuating disorder. So I'm comparing three cases.
Yeah, but the new one is so the kind of the static disorder is your statement that you see Anderson localization in the right plot, right?
Yep.
Which I don't.
Yes,
So
it's not. Yes. So from this example, it's this will not. If you are skeptical of Anderson localization, this example.
I'm not skeptical of anything. I'm just saying I don't see localization in the plot.
What you see here is that the wave function spreads much less than in the fluctuating case. You can see this already on the probability distribution, time evolution, which is shown in the top, and also in the bottom. So on the bottom, you can see the root mean square displacement as a function of time, which increases following roughly a square root of time curve for the fluctuating case. And this increase is slower for the static disordered case. So this is just a short example, short time evolution. So you can't really see that it goes to a constant. Actually, also on longer times, we don't observe it actually going to a constant. What we observe is that if we try to fit subdiffusion to this process and allow and we fit the exponent, then the longer we observe the process, the smaller the exponent becomes. So this is an indication of Anderson localization from time evolution. But I will have other arguments for Anderson localization in what follows.
Wouldn't it be also easy to just diagonalize the eigenvalue problem and then look at the eigenvectors and make some statistics and conclude maybe more clearly from them that
yes, we also did that.
Okay, thank you.
For example, the level spacing distribution, it follows Poissonian statistics. And I'm not even going to show that in this talk, but we show it in the paper with Arindam. Yes, I thought it's nice to show this time development or this time evolution illustration of Anderson localization. It gives one a concrete sense of what Anderson localization causes for the time evolution. But you are correct, this is not conclusive proof. Yeah. Okay, so Anderson localization has been observed also experimentally in laboratory simulations of quantum walks, like there's this early experiment from 2011, where they simulated a quantum walk by taking a strong coherent light pulse and recycling it using an optical fiber. And what they observed is that during the time evolution, they had these EOMs where they could switch something like a coin parameters of the quantum walk, and they could, by this rapid switching, they could realize either fluctuating disorder or static disorder for the quantum walk. And they found that indeed static disorder leads to Anderson localization. This is the measured probability distribution after a fixed number of time steps, semi-logarithmic plot. So you see that it has this exponential shape. What you don't see is that the width does not decrease over time. Whereas if you have a fluctuating disorder, then you have this inverse parabolic shape and a semi-logarithmic plot. This is like a Gaussian, and the width should increase diffusively over time. So what we found in 2015, we looked at examples where the two rotation operators, the one before the X and the one before the Y shift, they are related. For example, they are the same rotation operator. More generally, what we want is θ1 plus minus θ2 is equal to n pi, where n is an integer. And in these cases, even in the static disordered case, we don't see Anderson localization. Rather, we see a diffusive spread, just like we would if we had fluctuating disorder. So this is a numerical example which shows you this phenomenon.
Sorry, Janos, I have another question.
Please.
I mean, if you see diffusion in a two-dimensional random system, that doesn't necessarily mean that there is absence of Anderson localization. It could just be that the localization length is much bigger than the scales on which you observe your
Yes,
experiment, so to say. So how do you conclude that there is no Anderson localization?
this is correct. So our conclusion is based on explaining that this is a, So our conclusion is based on the fact that these special cases are cases where the quantum walk is a dynamical system which is tuned to a critical setting. So at the interface between two different topological phases. And so if you have, I think maybe I will come back to this at the end of the talk, because at this point I have not talked about these topological invariants yet. It will be easier to understand later. Anyway, this is the explanation that we gave with Jonathan Edge in this publication in 2015. And what you can see here is a cut. So this is a two-dimensional probability distribution, position distribution, and these are cuts showing on a semi-logarithmic scale, so showing the Anderson localized version and the diffusive version of the walk. For the diffusively spreading walk, we use the same coin before the x and the y steps, and the inset shows that the root mean square size of the wave function increases diffusively. So it's not just that it increases as a power law, diffusive or subdiffusive, but we see actually diffusive scaling. And I think I have something else switched on. I should probably just quit. Okay, sorry about that. So you can also see that there is a curious peak in the middle here. So the blue line, just as the dotted line, dashed line, they correspond to these diffusively spreading but completely coherent time evolutions. And you see that there is this curious peak in the middle. And at that time, we didn't quite know what this peak was or why it's there. Now we understand this much better, so I will also come back to this. So for the project with Arindam, we said, let's look at the the randomest quantum walk. So let's increase disorder to the maximum value, but no fluctuations. So let's let the coin operators be Haar uniform. So random IID coin operators for every site selected uniformly according to the Haar measure. And
sorry, again a question. So can you remind me again? Now this is more going into details. How you introduce which of the angles is disordered in your coin?
So for this example, well, we didn't randomize any of the angles. We just used this phi, which is at the end of the time step here, the phi over here. Whereas for the example of the Haar uniform coin, Haar random quantum walk with Arindam, there we randomized these R1 and R2 operators. And these R1 and R2, they are taking a general SU2 coins. So we have to make alpha, theta, and beta. We randomize all three.
Mm-hmm.
But in order to get uniform randomness according to the Haar measure, we have to take alpha and beta random equidistributed between 0 and 2 pi. But theta is not random equidistributed, but it is a transformed distribution. So we take zeta, which is random equidistributed, and we take theta as the arc sine of the square root of zeta. So that's the numerical recipe for obtaining a Haar uniform random SU2 operator. And it's enough to take SU2 because the global phase we can absorb in phi, which we also randomize. So we noticed that this quantum walk also spreads diffusively. On the bottom right, you can see a snapshot after 10,000 time steps, and on the right hand side you can see the white dashed line are the equi surfaces which come from a fitted Gaussian. So they fit quite well. And this is the same representation as in the work with Jonathan. We do cuts through this two-dimensional position distribution. And again, we find that overall, on a semi-logarithmic scale, we have an semi-logarithmic plot, we have an inverse parabolic shape. You can't even see the Gaussian fit because the red points, they lie on top of the Gaussian fit very nicely, except for the origin, where we again get this characteristic peak. And we also plotted in the same plot the fluctuating time-dependent disordered case of the same quantum walk, and a classicalized version where we replace the probability amplitudes with probabilities. And we see that the classicalized version and the fluctuating disordered version, they lie on top of each other, and both of them are reasonably good approximations of the Haar random quantum walk, except near the origin. So the question was, why does phase disorder appear to not localize the quantum walk with Hadamard coin? Hadamard coin was a special case of the fixed coin angles where the coin is the same after the first and the second shift. And the answer that we gave with Johnson Edge was that the Hadamard walk was a quantum dynamical system tuned to a critical point at the topological phase transition. And now we can ask, does this argument apply to the Haar random quantum walk? And our answer is yes. And to substantiate this answer, we also calculated the bulk topological invariance for the case with disorder, and we did some more in-depth investigation of criticality. So to explain to you what is behind this delocalization and why we think it is really delocalization and not just Anderson localization on a longer length scale, I have to tell you about topological phases. And I think I already told you about topological phases last time. So I can be a little bit quicker here, but if you want to interfere at any time with questions, very happy to answer. So topological insulators can be understood using the simplest theoretical model for insulators, which is just a gap insulator, sorry, a band insulator. So we have a bulk energy gap that separates fully occupied bands from fully empty ones. And the Hamiltonian, which models the behavior, is just a nearest neighbor hopping Hamiltonian on the lattice. However, there can be some internal degree of freedom. So these hopping amplitudes, they are not necessarily numbers, but they can be matrices, which also act on this internal degree of freedom. This framework can describe band insulators. It can also describe superconductors using the Bogoliubov-de Gennes trick. So if we, for any piece of insulator or superconductor, we are used to describing its behavior based on how it behaves in the bulk. And the bulk can be often well approximated by saying it is translation invariant. So we can say that eigenstates of the Hamiltonian, for example, they are plane waves. They can be characterized by momenta. So we can plot dispersion relations, plotting the dependence of the energy on the quasi-momentum. And if we do that, then we can check if there is a bulk gap separating fully occupied states from fully empty ones. And if there is a bulk gap, then we conclude that we have to do with an insulator, because if we try to excite the system by introducing an extra electron, there are no plane waves in the energy in an energy region which is accessible with small energy. If there are no plane waves, this means that we can put maybe an extra electron in the system, but only in a wave function which decays exponentially towards the bulk. So these extra electrons, they will not be able to go across the system. So we can have low energy electrons, but they are confined to the edge region. Topological insulators are distinguished by the property that it's not only that they can have low energy electrons confined to the edges, there can be eigenstates of the system there, but we know that there are eigenstates of the system which describe electrons confined to the edges. And we know because these eigenstates, they are not Anderson localized along the edge, rather they are delocalized along the edge. So they have exponentially decaying tails towards the bulk, but along the edge, a single wave function reaches all around coherently. So this is the distinguishing feature of topological insulators. And to simply understand how we can know such a thing, it's useful to consider the simplest two-dimensional example for topological insulators, which is a slightly altered version of the quantum Hall effect. This is called the Chiboujian model. In the standard quantum Hall effect, you have an electron which is hopping on a lattice, and there is a perpendicular magnetic field. And there you have to worry about how the strength of the magnetic field is tuned if you want to get a periodic description in real space of your system after you introduce the magnetic vector potentials. So the trick here is to use a magnetic field which is staggered, so there's no problems with periodicity on the lattice. And in the end, what this boils down to is a spinor particle, two-state particle, just like our quantum Walker, but instead of actively interfering and prescribing time evolution by unitary operator, here we just use a Hamiltonian to describe the dynamics. This Hamiltonian contains on-site potential U times sigma z. This is like a Zeeman term, and it contains nearest neighbor hopping on the lattice. But since we have an internal degree of freedom, two internal states, this nearest neighbor hopping amplitudes are not simply numbers, but they are matrices. And they correspond to spin rotation during the hopping. And these two spin rotations don't commute. So we have sigma z plus I sigma x over 2 for the x rotation, and sigma z plus I sigma y over 2 for the y rotation. This is a quite simple model. For example, you can put it on a cylinder or take periodic boundary conditions connecting the bottom and the top, but have open boundary conditions for the left and the right. And then we can diagonalize the system, and we find that there are the bulk states. Here, these are the black lines. But we also find that there are states which are in the bulk gap, and therefore they are exponentially confined to the right or to the left of the sample. These are indicated by the colors red and blue. And what you see here is that these states, they form branches of the dispersion relation, which describe states which propagate along the edge in one direction only. And such propagating edge states are called chiral edge states in the terminology of topological insulators. So they are one-way propagating up along the blue edge and down along the red edge. If we have such a one-way propagating state, then there is no way for it to be Anderson localized. It has to describe a wave function which spreads coherently all along the edge. And on the right, you can see illustrations of how these states look like in the transverse direction, so along the x direction. So topological insulators are called topological. You can already understand here that there is some topological feature, because if we have a band, a branch of the dispersion relation which connects the top band to the bottom band going down, then this is a small integer number telling you how many such branches there are. So this small integer number, it also corresponds to the observed current. If you connect such a sample from the top and the bottom, and you measure the current going across. And these small integers, they also characterize physics at the boundaries of one-dimensional topological insulators, three-dimensional topological insulators, arbitrary high-dimensional topological insulators. In 1D, these small integer numbers are is the number of topologically protected zero-energy states at the ends of a wire. For example, These are the Majorana zero modes, which Microsoft is planning to use for topological quantum computation. In 3D, this integer is the number of Dirac cones on the surface. Number here is always a net number. So if we have one edge state going down, we could also have one edge state going down, red, 2 going up. This would be like -1, 1 minus 2 is -1. And there's another reason to call these systems topological insulators. This other reason is if we look at the bulk instead of the boundary. So the bulk is, you can describe the bulk behavior by the dispersion relations, which I showed you, for example, here. This is a bulk dispersion relation. But when I show you how the energy depends on the wave number for the various bands, there is some information which I am not showing you here. Each of these points is an energy eigenstate corresponding to a plane wave with a given wave number, given energy, but also this system has some internal degree of freedom. I know it has some internal degree of freedom because there are many plane waves with the same wave number, but with different energies. So here I know that for this model, this internal degree of freedom has at least 5 different states which are available to it. So a single point does not only correspond to a given wave number and energy, but also a given ket vector, a given state in the internal Hilbert space, which is, in this example, 5-dimensional. In the simplest example, where we have 2 internal states, this internal Hilbert space is 2-dimensional. So there we have each of these plane wave energy eigenstates also has a qubit associated to it. And this qubit is a continuous function of the momentum k, continuous and periodic on the Brillouin zone. So you can imagine that the Brillouin zone, all possible values of k, they live on a torus. So to each point on the surface of the torus, we associate a plane wave. This plane wave has some given energy, but also it has a qubit associated to it, which can be represented on the Bloch sphere as a unit vector pointing in some direction. So in this way, to the bulk Hamiltonian, we can associate a hairy sphere, hairy torus. And then you can ask, is there some kind of topological invariant of this hairy torus? Are there different ways for the hairs to point which cannot be continuously, smoothly connected to each other? The answer is yes. You can count the number of skyrmions on such a hairy torus. And this counting skyrmions can be generalized using the language of Berry phases. So Berry connection, which can be defined for the nth energy eigenstate and the corresponding Berry curvature. And then the nth band has an associated topological invariant, which is the Chern number, the integral of the Berry curvature on the Brillouin zone. And the central beautiful idea of topological insulators is that these 2 topological invariants, the one describing the edge and the one describing the bulk, are connected. This is called bulk boundary correspondence. And I think I already advertised our lecture notes as an accessible introduction to this idea last time. Okay, I want to speed up a bit because I've already used up most of my time and I haven't got to the meat of the topic. So yes, quantum walks can simulate topological insulators via the effective Hamiltonian. And although it's not easy to write down the analytical formula for the effective Hamiltonian, it is possible to tune its symmetries. And this was shown in this very readable paper by Kitagawa and co-authors in 2010. They have shown how quantum walks, how the symmetries of the effective Hamiltonian can be tuned by changing the rules of the quantum walk, and how this can be used to realize all of the interesting symmetry classes in 1D and 2D as well. So realizing all of the interesting symmetry classes, I come back to the periodic table for a moment, also means realizing the class where there are no symmetries. So this is the periodic table of topological insulators. Here are the relevant symmetries. If there is a 0, it means that the symmetry is absent. And so the first row of the table is where there are no symmetries in the system. And this is interesting in 2D. This is where the quantum Hall effect lives. Also, this is where the two-dimensional quantum walk that we are concerned with lives. It is also interesting in 4D, 6D, any even dimensions. You have some bulk topological invariant connected to some robust surface behavior. So the split-step quantum walk, which we consider two-dimensional split-step quantum walk, as Kitagawa realized, he was a PhD student at the time at Harvard. So he realized that this has some topological invariant, but it wasn't clear what the invariant is. He saw topologically protected edge states at an interface between two different bulks. This is indicated here, but at that time, it was not clear what the bulk invariant is. The Chern number was 0 for these quantum walks. It was not the Chern number. So we answered this open question by showing that this extra bulk invariant, it can be mapped onto this Rudner quasi-energy binding, which was an invariant introduced in 2013 by Mark Rudner and co-authors in PhysRev-X. So in this simple toy model explained in Mark's paper, I want to take a little time to explain it because it's fun and you can easily understand what's going on here. And this is quite closely related to the two-dimensional quantum walks that we consider. So here, this is a nearest neighbor hopping Hamiltonian. There are no on-site potentials. And we have full control over the nearest neighbor hopping terms. So we switch off all nearest neighbor hoppings except for the red hoppings, then the blue, then the green, then the yellow. And we carefully time the periods when these hopping amplitudes are switched on in such a way that we realize a pi pulse. So if we had a particle which was initially on this black site over here, for example, then its wave function will go over completely to the neighboring white site in the first quarter of time evolution. Then it will be transferred to this black site, then to the left to this white site, and then back to this black site. So during time evolution, its wave function underwent circle. But if I only look at the net effect, then it started from this black site and it ended up at the same black site. So therefore, if I take some wave function, which is a superposition of many sites, some complicated shape, then during time evolution, this complicated shape will somehow change. But after one complete cycle, it will come back to the same shape as it had in the beginning. So therefore, it is, as long as we consider the bulk, things in the bulk, the effective Hamiltonian is just like doing nothing, just 0. However, if you consider what is going on at the edges, we find a different picture. Let's consider this black site, for example. After the first quarter, it goes over to this white site. Then it stays there. There are no hopping amplitudes which are switched on going from this site. Then it is transferred to here, and then it stays there. So during one complete time step, it was shifted by two sides. So particles in the bulk, they go around in circles, clockwise. On the edge, they are shifted, and the shift direction is counterclockwise. So if you represent the dispersion relation showing both bulk and edge eigenstates, and you see that the bulk eigenstates are just a constant 0. No, for the effective Hamiltonian, there is no time evolution. And but the edge eigenstates, they are represented by these strange linear lines, which are allowed because we don't only have quasi-momentum here, but also quasi-energy. So pi is the same as minus pi for both quasi-momentum and quasi-energy. So so these edge states are topologically protected. They cannot be removed by smooth deformations of the dispersion relation, and the topological invariant associated with this probes not only the net effect of what is done, so not only the bulk effective Hamiltonian, but also how it is done. So we do time slicing of the unitary time-step operator, and then we do an integral over these time slices. This is a three-dimensional winding number. Okay, so we have shown that this winding number, after mapping to Hamiltonian, this winding number is also behind the topological invariance of the quantum walk, and it also explains why a quantum walk with parameters exactly at the interface between two topological invariants, it cannot be Anderson localized. If it was Anderson localized, then in a setup with unfortunately I didn't show this picture here, but I can show it at the end of the talk. So you can think of a simple Gedanken experiment, which shows you that you have to avoid Anderson localization, at least on the interface between two different topological phases. Okay, so the global phase phi does not change the topological invariant. Adding a global phase to this process would shift everything up on the quasi-energy, in the quasi-energy direction. So things that were at the top will come back at the bottom. So just a twist. And this doesn't change the direction of propagation of the edge states. So you might think that if you now take a randomized phi, then the topological invariant also survives this phase disorder. And this is something that we believed to be the case in 2015, but we didn't show numerically that this is true. And this is something that we address now in this work with Arindam. So we have a formula for the bulk topological invariant in terms of a winding number here at the bottom. And this is a winding number which is an integral over time over quasi-momentum along x, quasi-momentum along y. So this is well defined for the translation invariant case. If you want to generalize this for the case without translation invariance, for example, where this phi breaks translation invariance of the time-step operator, then these dkx, dky integrals are no longer well defined, and we have to do something else. Either we have to reach for more complicated tools like non-commutative geometry to define these integrals, or we can do something different, namely use scattering setups. And this is what we did with Arindam. So we said if there are topologically protected edge states, they will identify themselves by quantized signatures in scattering. So we take quantum walk, it will describe the scattering region of a scattering setup. We attach leads on the left, semi-infinite lead on the left, semi-infinite lead on the right. So in the lead, we use the same recipe for the quantum walk as in the bulk, except there are no rotations. So there's only an x shift and also no y shifts to keep things simple. So in the lead, in both the left lead and right lead, all that we do are spin z dependent shifts along x. So there are simple modes. Spin up particles are always transferred to the right. Spin down particles always transferred to the left. So if we put a particle into the left lead, it will be taken towards the scattering region. There it will undergo some complicated time evolution. Eventually, it has to come out, emerge of the scattering region, either reflected to the left or transmitted to the right. And what we need to do in order to observe topological invariance is to introduce some interface into this scattering region. And we did that by so-called cut. So we modify the coin operators in the scattering region in a small part, for example, of two rows of sites. We modify it in such a way that it is either theta 1 is 0 and theta 2 is pi half, or theta 1 is pi half, theta 2 is 0. These are special cases where the particle cannot penetrate across such a black region. So this is a cut in the sense that it is it is not you can't go through it. So you have to be reflected from this black region, but for this reflected parts of the wave function, it can happen that you skip along this black region in kind of skipping orbit motion. If there is such a skipping orbit state, this is a topological protected edge state. And if there are such edge states, they will contribute to conduction. So these are time evolution pictures. What happens to particles which are injected at the left at various points with respect to the cut. If it is injected below the cut, then you can see that most of the wave function is reflected immediately. Some of the wave function spends some time in the system, but eventually it comes back. If the particle is injected just above the cut, then some part of it is reflected, but during time evolution, a large part of it gets transmitted across. And if it is injected well above the cut, it's a bit harder to say. A lot of it is reflected, some is transmitted. So these are time evolution pictures. What we can also do is we can take Fourier transform of these time evolution pictures and thus obtain zero quasi-energy scattering states. So zero energy or any quasi-energy by taking Fourier transform. I'm showing you here the zero quasi-energy scattering states. So these are eigenstates of the whole unitary time-step operator, eigenstates in the leads and in the scattering part as well. And from these eigenstates, it's easy to read off what the transmission probability is. And the transmission probability for an eigenstate corresponding to input below the cut is quite small. Here it's 7 times 10 to the minus 8 for this finite size sample. Just above the cut, it is more substantial, so 14% transmission. Whereas well above the cut, it is, in this case, 0.5% transmission. So there is nothing quantized here. But what you can do is you can take linear combinations of these zero energy scattering states and try to obtain states which are perfectly transmitted. And this is possible. You can write down the transmission matrix at any quasi-energy. You can reconstruct it from this transmitted energy, transmitted parts of the wave function by Fourier transform. And then you need to diagonalize the T dagger T matrix. So in this way, what we find is that, for example, for this numerical example, with this distribution of disorder, these are the two eigenstates which correspond to perfectly transmitted states. You can see that they are perfectly transmitted because I'm using here color to denote spin value. So spin up is red, spin down is blue, and something in between has both spin up and spin down components. And you can see that in the leads, these are perfectly spin ups. So there is no reflection here, or practically no reflection. Almost everything is transmitted. So there are these two perfectly transmitting states. These correspond to the edge states. So here we are fine-tuning where we inject particles in such a way that we couple perfectly to the edge state channel, and therefore we get unit transmission. And since we are interested in disorder averaging, what we can do is we can average over quasi-energy, because in our system we have the phase fluctuating between 0 and 2 pi equidistributed. This means that essentially we are removing all quasi-energy information from the system. Every quasi-energy is statistically equal. So we are perfectly fine with averaging over all quasi-energies, and it's this makes life very easy because averaging over all quasi-energies is the same as just summing over all times. So there is this extremely simple formula. You can just do time evolution and sum the absolute value square of the wave function which you obtain for all times. And what you get is a probability distribution which looks like this for this concrete example. And if you sum the values that you find at a fixed x value in the output lead, and this sum comes very close to a quantized value, not exactly quantized because we are taking some finite time example, and also not exactly quantized because we have some transmission across the bulk. So we have finite size and finite time corrections. In any case, this is a quite numerically efficient way of obtaining average transmission. And this average transmission turns out to be well quantized. I'm also looking at time. I'm doing very poorly with time, so I will speed up. We found that using this tool works really well. It allows us to conclude that indeed the bulk topological invariant for the case where the angles theta are fixed, but we have phi, this extra phase which is disordered, is the same as if we didn't have any disorder on this phi at all. So what we can now do, I present a hand-waving argument, which is taken from the quantum Hall effect. It's the same type of criticality, critical situation, as in the quantum Hall effect. So we consider now the situation of the Haar random quantum walk, where it is not only this phi, which is disordered, but also the values θ1, θ2, so the rotation angles. So if θ1 and θ2 are disordered, then in some parts of the system, we have values of θ1, θ2 with a topological invariant of -1. These are the green parts. And in other parts of the system, we have +1. And if these disordered values of θ1, θ2 are such that overall it is statistically more likely to have a topological invariant of +1, then we have these islands of -1 in a sea of +1. So overall, there are no edge states which correspond, which help conduction of the particle. We have an insulator here. Actually, it's an anomalous Floquet-Anderson insulator with Q of +1. If we have mostly -1, so not only islands here, but these islands, they coalesce and they form a continent, and there are some small puddles of +1 in between. Then again, we have edge states on the shores of these puddles, but these edge states don't reach across the system. So we have an insulator. This is an anomalous Floquet-Anderson insulator with a different topological invariant, a -1. But in between these two situations, where we have islands in a sea and we have puddles on the land, we have a situation where it's the same statistical weight of +1 and -1. So these shorelines, they coalesce, they form a percolating network of edge states. So in this case, we have conduction. And it's the same picture as in the integer quantum Hall effect. The similarity with the integer quantum Hall effect can be put on a more firm ground using field theoretic tools, this recent paper by Altland and co-workers. And in this argument, I said we have the same weight, +1 and -1, but I didn't tell you what the statistical weight is, how it should be calculated. It's not, and this, as far as I'm concerned, this is an open question. The analogous question for the one-dimensional case, we could answer analytically with Tibor Rakowski in 2015, but for this 2D case, it's an open problem. Okay, so we have this critical case in between the two. So all three of these are disordered, but this is disordered in a symmetrical way. And somehow this Haar random rotation coin also corresponds to this symmetric disorder. We have equal weights of the +1 and -1 cases. I'm showing you the level spacing distribution here. So this is normalized level spacing on the horizontal axis, the corresponding probability density on the vertical axis. You can see that it fits quite well with the Gaussian unitary ensemble, Wigner-Dyson. You can also see that it departs from Wigner-Dyson for large level spacings. You can see it also here, but better here on this semi-log plot. And actually, such effects have been also seen in the quantum Hall effect. And more concretely, we can characterize the critical behavior by computing critical exponent eta. This critical exponent, it controls the multifactoriality of the wave function. Actually, we only take the q equals 2, so we didn't do a full multifactoriality analysis. We only took one power here. Multifactoriality would be when we take the q's power of the box averaged p values probability distribution. So this is diagonalizing the unitary operator as suggested by Sergei, and doing a statistical analysis of the wave function. We find that indeed it is fractal, and the exponent is in good agreement with the value expected from the quantum Hall effect. So this is for the quantum Hall effect, it should be this p squared expectation value, which should scale like L to the 4 minus eta. We find it scales the power law, and eta 0.55 plus minus 0.02. In the quantum Hall effect, it's 0.52, so it's pretty much the same. We can also do the autocorrelation. Look at the autocorrelation function of the position distribution. Again, for the quantum Hall effect, this is expected to fall off as a power law with eta. We find that it does fall off as a power law with eta, and the least squares fit gives value compatible with 0.52. And finally, there is this peak in the origin. So the plateau here should decrease like 1 over t, because this is a diffusively spreading wave function. So its size scales with the square root of time. It's two-dimensional. So we have square root of t times square root of t is t. So the total size of the 2D wave function scales like t. So therefore, its value should decrease like 1 over t because it is normalized. And this is indeed the case, except for this peak in the middle. This does not decrease like 1 over t. This decreases with an anomalous power law. This is also predicted for the quantum Hall effect. And we observe this power law, and the fitting is compatible with 0.52. So that's all I wanted to tell you today. Quantum walks, they spread quadratically faster than random walks. This makes them interesting for quantum algorithms. But with quenched phase disorder, the tables are turned. And quantum walk does not spread faster than a random walk. In fact, it spreads slower. Asymptotically, its spread stops. Whereas the random walk, it spreads diffusively. But there are special cases. So yes, these cases where we have Anderson localization, so the spreading stops, they are Anderson localized cases, but with a bulk topological invariant. And this bulk topological invariant is the Rudner binding number. Correspondingly, there are these Anderson localized phases, they host chiral edge states. Moreover, they are anomalous Floquet-Anderson localized, Floquet-Anderson insulators. So the bulks are completely localized. There is no, in Chern insulators, there is always some energy value where the localization length diverges. Here, there's no such energy value. So the bulk localization length is finite. There are some exceptions to this localization. And these exceptions are if the parameters theta are fixed so that we are exactly at a topological phase transition. We are in the process of changing the bulk binding number from +1 to -1. Then somewhere along the way, we must be exactly at the boundary. And if we sit at the boundary, then we cannot be Anderson localized. We must have the classical picture is that we have a percolating network of edge states, and so therefore we must have these critical situations, and we can also have this interface between +1 and -1 not only for the cases where θ1 and 2 are fixed, but also where θ1 and 2 are disordered. So we have fully disordered θ1 and 2, but the distribution of the disorder changes from one topological phase to the other. Then we can have a critical situation in the middle. And this is what happens for the Haar quantum walk. And we have substantiated this explanation by doing some critical analysis. Namely, we calculated this critical exponent eta by 3 different numerical ways, and we found that it is compatible with the universality class of the integer quantum Hall effect. With that, thank you for your attention and happy to have questions.
So thank you, Janos, for this talk. Yes, and I think we are ready for questions from the audience.
Let me maybe start with a very basic one, coming back to what we discussed before. I'm still thinking all the time about this nice effective Hamiltonian with hoppings which decay exponentially along the system. How would I, from what would I see that? I mean, so I have of course, the dispersion relation of the quantum walk, yes, and then so basically what you say is that you expand it in a Fourier series and with K, and then you see that there are, I never looked at that. So there are arbitrarily large non-zero coefficients in the series, you say, which simply decay exponentially, right? Is that
Yes. So if we did not have those, then the dispersion relation would just be like cosine or sine, but we don't only have cosine and sine, but we have cosine 2k, sine 2k, cosine 3k, sine 3k. This indicates the presence of second, third nearest neighbor hoppings. And so we have longer range hoppings, but we also know that they must decay exponentially because the dispersion relation is smooth.
Yeah.
Thank
you.
Okay. Janos, maybe a simple question here. So if I think about these driven systems that you were talking about during the end of your talk, you described this particular case where you have to drive in a specific way to come back to the origin, and that has certain topological properties. But equivalently, I could take something like a 1D model, which I know is topological in the undriven system, go to the high frequency limit, even when it is driving, and this generally just renormalizes your model, right?
Yes.
So in that case, you don't need some really complicated sort of driving protocol, but you would still have certain topological invariants. How do these two pictures connect in some way? I mean,
so you could also do that. You could apply. So here the time averaged Hamiltonian, the very in this example, the time averaged Hamiltonian is a very poor approximation of what the actual dynamics is. The changes in the Hamiltonian are substantial from one part of time evolution to the next.
Right.
And also these changes are slow. So we are not in the high frequency limit and we are not in the perturbative limit here.
Right.
There's a lot of work on using high frequency perturbative changes like what is called shaking the lattice in order to induce topological behavior into Hamiltonians whose topological invariants are trivial. And this is very valuable work. It allows us to tune the topological invariants. Here something different is done. So this topological invariant, this finding number, it's not only that we tune its value, it's also that it doesn't really make sense to calculate this for a time-independent Hamiltonian. Its value cannot be changed by driving in the high-frequency perturbative limit. We have to go into this deeply non-perturbative regime, low-frequency, high-intensity drive. So this is a qualitatively different scenario.
So there is no way to, or is there some kind of a model that would sort of allow me to go from one picture to the other in a nice continuous manner, or such models don't just exist? I mean, they're as you said, they're completely different scenarios, and we should just think of them as differently.
But you could take this model and you could So you could consider, for example, yes. So you could consider, for example, this this Chiboujian Hamiltonian, this simple toy model for a Chern insulator, but with parameters which are tuned in such a way that there are no edge states in the bulk gap.
Yeah.
So non-topological value. And then you could say maybe there's a way to shake the lattice to introduce high frequency tuning to the parameters and nudge the system from this non-topological case, allow it to close the gap and reopen, and let topological protected states appear. And this is fine. In order to get to this other type of topology where the edge states, they go entirely across the Brillouin zone, not only in momentum, but also in quasi-energy. For this, you have to also close and reopen the energy gap at the edges of the Brillouin, of the Floquet-Brillouin zone. So this means that using high frequency perturbations alone is certainly not enough. You have to come down with the frequency of your perturbations. So you could do this in a continuous way, but the tools which are useful in the high frequency limit, like the Magnus expansion, are no longer useful in this non-perturbative limit. So you could do this smooth connection, but the description of the one and the other limit, for the descriptions, if you want to simplify your tools, then you need different tools for the one and for the other limit.
Yeah. Thanks a lot for that.
Welcome.
Okay. Any more questions from the audience? So I don't see any more hands raised. I think we already had a lot of questions even during the talk. So let us all thank our speaker once again for this wonderful talk.
Enjoyed the discussion with you. So I was happy to give this talk. And if anybody is interested to continue discussing, I'm available.
Yeah, so maybe we can have a look. So let's have a 5 minutes break and see how many people survive in this meeting room. And then we can carry on from there.
Good. So see you in 5 minutes.
Yeah, thank you all for joining in then. And see you in 5.